let's dive into the fascinating world of machine learning, starting with its fundamental principles and concepts. Our goal is to understand how machine learning helps us unlock valuable intelligence and insights from raw data. Today, we'll explore the key differences between supervised and unsupervised learning, two fundamental machine learning paradigms. We'll focus on their key distinctions, looking at the types of data they use and their overall problem-solving approach. First, let's consider supervised learning, a widely used approach where the model learns from labeled examples. It specifically requires labeled data, meaning each input is paired with its corresponding correct output. The primary goal here is to predict a specific output variable based on the patterns learned from the input data. Now, let's turn our attention to unsupervised learning, which takes a different approach to data analysis. Unlike supervised learning, it works with unlabeled data, meaning only inputs are provided without any predefined outputs. The main objective is to discover hidden patterns, underlying structures, or relationships within the data itself. Let's look at some common algorithms associated with both supervised and unsupervised learning techniques. For supervised learning, we have algorithms like linear regression, support vector machines, and decision trees. In unsupervised learning, examples include k-means clustering, principal component analysis, and the a priori algorithm. Finally, let's explore some practical use cases where these different learning approaches are applied. Supervised learning is excellent for tasks like spam detection and predicting stock prices based on historical data. Unsupervised learning is often used for customer segmentation and identifying unusual patterns in anomaly detection. Let's explore unsupervised learning in more detail, understanding how it operates without explicit guidance. Our focus is on how this method helps us discover intricate, hidden structures and relationships within complex datasets. A defining characteristic of unsupervised learning is its reliance on unlabeled data for analysis. It processes data without explicit outputs, learning patterns solely from the input features themselves. The core goal here is the discovery of inherent patterns, rather than predicting specific outcomes. It aims to uncover underlying structures, groupings, or associations that naturally exist within the dataset. Clustering is a primary technique in unsupervised learning, grouping similar data points together. For example, it groups similar data points, like customers for segmentation, often using algorithms such as k-means. Association rule mining is another important unsupervised technique for finding relationships. It finds relationships between different variables, like in market basket analysis, often employing the a priori algorithm. Dimensionality reduction helps simplify complex datasets by reducing the number of features. This technique simplifies data by effectively reducing its features, with principal component analysis, or PCA, being a common example. Now, let's walk through the typical flow of a supervised learning process step by step. We'll see how it moves from initial labeled data all the way to generating accurate and reliable predictions. It all begins with labeled data input, where each example has a known correct answer. Next, the machine learning model undergoes training, learning patterns from this labeled dataset. The model then generalizes these learned patterns, making it capable of understanding new, unseen data. After training, the model is ready for its prediction task, applying what it learned to new inputs. Finally, the output evaluation step assesses the model's performance, checking the accuracy of its predictions. Let's explore how algorithms help us make predictions using data in various scenarios. We'll dive into two fundamental prediction algorithms: linear regression and the k-nearest neighbors, or KNN. First up, let's understand linear regression, a powerful and widely used statistical modeling technique. The formula for linear regression is y equals beta naught plus beta 1x plus epsilon. In this formula, y represents our dependent variable, which is the value we are trying to predict, and x is our independent variable, also known as the feature that helps us make that prediction. Beta naught represents the y-intercept, which is a constant term where the line crosses the y-axis. Beta 1 is the coefficient of our feature x, indicating the impact x has on y. Linear regression models a straight-line relationship between these variables, which is quite intuitive. It works by finding the best fit line that minimizes the overall error between predictions and actual values. This algorithm is primarily used when we need to predict a continuous numerical value, like price or temperature. Next, let's explore k-nearest neighbors, or KNN, focusing on its core concept of Euclidean distance. The Euclidean distance formula is d equals the square root of the sum from I equals 1 to n of x sub I minus y sub I squared. Here, d is the direct distance between any two given points in our dataset. X sub I represents the value of feature I for the first point we are considering. Similarly, y sub I is the value of feature I for the second point we are comparing, and n simply denotes the total number of features or dimensions describing each point. This formula measures how similar two data points are by calculating the straight-line distance between them. It forms the fundamental basis for how KNN selects its nearest neighbors to make predictions. Interestingly, KNN is versatile and can be applied effectively for both classification and regression tasks. Today, we'll examine support vector machines, or SVM, and delve into crucial model trade-offs. We'll focus on how SVMs optimize data separation and achieve strong generalization capabilities. Let's start with the hyperplane, a key concept in SVMs that defines our decision boundary. It is essentially the line or plane that clearly separates data points belonging to different classes. Next, we have the margin, which is vital for the model's robustness and performance. The margin is the distance between the hyperplane and the closest data points, known as support vectors. Maximizing it improves generalization. Support vectors are those critical data points that directly influence the position of our hyperplane. These are the data points closest to the hyperplane, and they are crucial for defining the margin. The kernel trick is a clever technique used when data isn't linearly separable in its original form. It maps non-linearly separable data into a higher dimensional space, making separation possible and easier. Finally, let's discuss the bias-variance trade-off, a fundamental concept in machine learning model development. It involves balancing model simplicity, or high bias leading to underfitting, with complexity, or high variance leading to overfitting, for optimal performance. Let's learn how to quantify the performance and accuracy of our machine learning models effectively. We'll cover key metrics like accuracy, precision, recall, and the F1 score with their respective formulas. First, let's look at accuracy, one of the most common and intuitive evaluation metrics. Accuracy is calculated as the number of correct predictions divided by the total number of predictions made by the model. Here, correct predictions are the sum of true positives and true negatives, and total predictions include true positives, true negatives, false positives, and false negatives. Accuracy measures the overall proportion of correct predictions that your model has made. It works well and is a good indicator when you are working with balanced datasets. However, accuracy can be misleading, especially when dealing with highly imbalanced class distributions. Next, we have precision, a metric that focuses on the quality of positive predictions. Precision is calculated as true positives divided by the sum of true positives and false positives. True positives, or TP, are cases where the model correctly predicted a positive outcome. False positives, or FP, are cases where the model incorrectly predicted a positive outcome. Precision tells us the accuracy of our positive predictions among all the positive predictions made. This metric is particularly important when the cost of making a false positive prediction is high. Keep in mind that precision does not take into account the false negative predictions. Now, let's look at recall, which measures the model's ability to identify all relevant instances. Recall is calculated as true positives divided by the sum of true positives and false negatives. False negatives, or FN, are cases where the model incorrectly predicted a negative outcome. Recall indicates the model's ability to successfully detect all the actual positive cases. This metric is crucial when the cost of missing a positive case, a false negative, is very high. Maximizing recall can sometimes lead to an increase in the number of false positive predictions. Finally, we have the F1 score, which offers a balance between precision and recall. The F1 score is calculated as 2 multiplied by the product of precision and recall, divided by their sum. It represents the harmonic mean of both precision and recall, providing a single score. The F1 score effectively balances the importance of both precision and recall metrics. This metric is particularly useful when you are working with imbalanced datasets. It gives us a single, combined metric that is easier to interpret for overall model performance. Let's explore K-fold cross-validation, a robust technique for assessing your model's performance. We start with our complete original dataset, which contains all the information we have. In K-fold, we divide the data into K equal parts. Here, fold 1 serves as our test set. The remaining folds, from 2 to 5, are then combined to form our training dataset. We then proceed to train our machine learning model using this designated training data. After training, we evaluate the model's performance on the unseen test fold to measure its accuracy. This process is repeated K times, with each fold taking a turn as the test set. All right, let's bring everything together now with a quick summary of the key concepts we've explored today. Here are the most important takeaways, the essential points you should remember from our discussion on machine learning basics. Remember, machine learning fundamentally enables systems to learn directly from data, continuously improving their performance over time. We differentiated supervised learning, which uses labeled data for predictions, from unsupervised learning, which finds patterns in unlabeled data. We also discussed fundamental supervised algorithms like linear regression, k-nearest neighbors, and support vector machines for various tasks. Crucially, metrics like accuracy, precision, recall, and F1 score are indispensable for evaluating your classification model's effectiveness. Cross-validation is a vital technique that helps us assess how well a model generalizes to new data and reduces overfitting. Finally, we tackled overfitting and underfitting, understanding how regularization and early stopping are key strategies to overcome these challenges.